do, I welcome you all to the UNU-INWEH public event, the Science Talk. If you're joining us for the first time, we're happy that you are here. I am your host, Professor Grace Oluwasonya. A bit of housekeeping. Before presenting our distinguished speaker, please note that there will be an interactive Q&A session at the end of the presentation. At that point, there will be room for comments, Q&A, and any other contributions that you may want to share. Please type your questions or comments in the Q&A chat box. We will pick it up from there afterwards. Thank you. The topic of today's talk is mapping surface water dynamics with cloud computing and open source software. So let's talk. Our presenter is Dr. Wu. I will avoid calling his first name so that I won't have to massacre it. It will tell you by himself the correct pronunciation. Its research focuses on leveraging big geospatial data and cloud computing to study environmental changes, particularly surface water and wetland inundation dynamics. At UNWEH here, he is a senior research fellow in geospatial data science and open science software development. He's also an associate professor at the Department of Geography and Sustainability at University of Tennessee, USA. He has developed several open source packages designed for advanced geospatial analysis and visualization. A couple of that is the Gmap and leaf map and some segment geospatial packages. His open source contributions are available. I'm sure he's going to share some of that with us. So without further ado, Dr. Wu, you are welcome. The floor is yours. Thank you.
Thank you, Grace, for the introduction and the invitation. So for today, I'm going to show you some of the resources that you can use to map the surface water using cloud computing and also some open source software packages. So you will just need a browser, and then you can easily use open access data and cloud computing to just see the changes around the surface water changes around the globe. The link to my slides can be accessed by scanning the QR code, or you can visit the URL, bit.ly UNU-talk. And here is the outline. First, I will briefly introduce some of the Earth observation data that you can use to map surface water. And then I will introduce Google Sensing, the cloud computing platform that can empower surface water mapping, and some of my previous work on mapping surface water bodies using aerial imagery and also satellite data. Then I will introduce Gmap, the Python package that can help you much easier to utilize cloud computing and also visualization. I will also show you some additional resources if you want to learn more. And lastly, I will give you a demo showing you how you can actually use some of the tools that I developed, and then you can adapt and then to use to map the surface water around the globe. And at the end, we have time for question and answers. Upper right corner here shows you the link where you can actually create animation like this easily without coding. So on the left side here shows you basically the river dynamics. On the right shows you the extraction of surface water body using cloud computing. And just a couple minutes, you can get the result, and you can analyze the dynamics of surface water on the surface. So in order to monitor these changes, we certainly need Earth observation data. So there are a lot of satellites that have been launched in the past, either by NASA, by ESA, and some of the common ones I'm going to cover you, show you later. But you can see the whole fleet of satellites that have been launched, and some of those are dedicated for surface water, some for land cover. But there are a lot of satellites we can use to monitor surface water. And also this one is from ESA, and the popular one include the Sentinel 1 and 2 and 3 and 5. So those are the satellites that have been launched in the last couple of years, and it has empowered a lot of environmental applications. And here's a table showing you some of the popular ones being utilized to make either land cover or even surface water body. And the longest one we have is Landsat launched by NASA. So it's 30-meter resolution since the 1980s. And so right now we have Landsat 8 and 9 in operation. So we roughly get 16 days revisit frequency. So if you have two satellites running at the same time, so we can get roughly 8 days. So we can think about we have weekly global coverage of satellite data from Landsat. And also we have the MODIS data. That one is coast resolution 1 kilometer, but also back into the 2000. And the nice thing about this is the temporal frequency is higher. And more recently, NASA launched the SWOT satellite, surface water and ocean topography. That one you can get also 30-meter resolution, 21-day revisit frequency, and it's dedicated for surface water, so it's not for land cover or other types, and mostly for surface water. So these are the three commonly used satellites for mapping surface water body at the global scale. The other two are the Sentinel-1 is the SAR data from European Space Agency, also Sentinel-2. That one is 10-meter resolution, so it's a high resolution, but it has a shorter time span, so it's only back to the 2015, so it's not a very long time period compared to Landsat, but they complement each other. So Sentinel-2 has a 5-day revisit frequency compared to Landsat that has 16-day, and also it has a high resolution. So these are some of the common one, and later I'm going to show you some of the application can utilize some of this data. So these are all available on the cloud computing platform, so you can just use those. You don't have to download any data to your computer. So Google Engine is a cloud computing platform. Before we get into detail, just for those of you who are not familiar, basically just a cloud computing environment that you can use to access data and then analyze data. So you have never used cloud computing, I think you must have watched YouTube movies on YouTube or Netflix or whatever. So these are some of the cloud computing environments. So nowadays you don't have to buy the DVD, you don't have to have a fancy computer. All you need is just a browser. Then you can start watching the movie at high definition. So it's streaming things on the fly. And so in the geospatial domain, we have the major key player, for example, Google Engine, Microsoft, and also AWS. So those are the key three players. And right now, the Google Engine platform is the most popular one, and it's free for research, education, and also non-profit. You can sign up for an account. Upper right corner here, there's a link. It's very powerful. So it was launched in 2010, almost 15 years from now. And in the last couple of years, it has seen dramatic increase in the usage. So here's just a histogram showing you like how many people are using that to do scientific studies. And in the journal publications, you can see the exponential increase in terms of the using Google Engine for earth science applications. And it has a very user-friendly database, and it has over 100 petabyte data catalog. So it's huge. Most of the commonly used data are already there. But you do need to know some coding. So it supports Python, JavaScript, and also REST API. But it's not very complicated. So it's really, they have very comprehensive documentation, and it's also free, so you don't need to pay anything for doing your research. It's also reproducible and accessible. So I'm going to show you some of the things that later in those demo, you will see how reproducible it is and accessible. And one simple application using Google Engine is that, for example, you can process a lot of satellite data. Just use a couple lines of code, and then you can, for example, let's say we have tons of satellites collecting by satellites every day, and some they have cloud, some might not have cloud, and you can use Google Engine to process a lot of imagery, and then you can create this kind of cloud-free imagery, literally just one line of code if you have enough data. And it's very powerful, very easy to use. You don't have to download data. All you need is just a browser and a couple lines of code. So some of the things that imagery that you see, for example, if you go to Google Earth, looks perfect, looks cloud-free. Those images mostly have been processed by cloud computing, Google Engine, and other AI platforms. And it's not real because every pixel comes from a different date. Okay, so every pixel is a base quality pixel for that location. So if you put all the base quality pixels together, you end up with an imagery like this, and it's very, very nice. And you don't have to do that on your own. You just use the cloud computing to process the data. And as I mentioned, so Google Engine has a huge data catalog, over 100 petabytes, basically 1,000 terabytes. And I don't think you can any individual can handle this amount of data or store this kind of amount of data. And it's has including most of the commonly used satellite data. If the data that you want to use not available there, you can also upload data to your account, and then you can use the cloud computing power on the platform to process a large amount of data. And it keeps growing, so it's actually taking all, ingesting all the latest data into the database. So you always keep up to date, and in that way, you don't have to go to NASA or the ESA to download data on your own. So basically, you don't have to go to the store to buy the DVD. You just watch movie on Netflix or YouTube. That's it, and you get the latest one. It keeps synchronizing, so it's pretty good. And so if you're still using the traditional way to process data, you have not really been utilizing Google cloud computing or any cloud computing yet. You might want to prepare yourself in the next NASA Landsat satellite mission. So right now we have Landsat 8 and 9, so it's 11 spectral bands, 30-meter resolution. Landsat next is going to be launched in 2030, 7 years from now, so it's going to increase to 10-meter resolution and also more than double the spectral bands to 26. So right now, one Landsat image is just 1 gigabyte. It's okay still if you want to download the data and then process on a local computer. But in 6 years, you will not be ready because the image will be 20 gigabytes. So it's going to take you tons of time to download the data. And even if you can download the data, I'm not sure if you have the computing power to process 20 gigabytes. It's just one imagery. So think about if you're doing for a county, for a whole country, or for a whole continent, or at the global scale. It's going to be many, many terabytes, and you will not be able to actually handle this kind of data when it's the satellite being launched. So people are going to basically utilizing cloud computing to process. You probably just sitting there watching people doing things. So you definitely need to think about, it doesn't have to be Google sending, but it must be some kind of cloud computing platform that can help you process this kind of data at scale. You will not be able to handle that. Even the technology changes, improve, and also the hardware, but it's not going to catch up with that kind of storage and also the memory. So I just want you to keep that in mind. Please prepare yourself for the next generation of cloud computing. And so next, I'm going to quickly introduce some of the service water mapping that work that I have done in the past. I've done some work on mapping wetlands in the United States in the region called Prairie Pothole. So it has a lot of smaller wetlands, something like this. It's pretty small, less than 2 Landsat pixels. The median size is only 1,600 square meters, and it's also very shallow. So it's very dynamic. The water body changes all the time throughout the season. But these are very important ecosystems that support a lot of vegetation and also wildlife species. And it's very important, but we don't have a lot of data actually for the area. So USDA, the United States Department of Agriculture, they have area imagery acquired every 2 to 3 years, covering the entire US. So this one just show you some of the time series, and you can clearly see the dynamics of these wetland water bodies. So the yellow arrows in here. So in the dry year, you can see separated. In the wet year, they are all connecting. So it's very, very dynamic. And how can we utilize this high resolution? So it's 1 meter resolution or 30-meter resolution, very fine resolution. And here's also show you the dynamics, so you can see the animation like during the throughout the years. So we have data back into 2009. So every 2 to 3 years, you get one imagery, and this is what the data we already have. But it's still underutilized. Not many people are using that to do this kind of service water body, and because the computation is very intensive. And just going to show you some of the existing data. So we have some existing data also from cloud computing. It's called a JRC. I will cover more later. Is you can map the service water extent by months. Basically, you have monthly data, and you can see the boundaries of those water bodies. So it doesn't match very well with the water body. Also, it meets some of the small service water bodies. On the right here shows you the the U.S. Fish and Wildlife Service, the National Wetlands Inventory. So that one was manually delineated in the 1980s. So you can see now the water body actually expand to much larger in this particular area. And the boundary doesn't really match with what we have right now. So using cloud computing, we can easily use those high resolution imagery. We can automatically delineate the water boundary. And besides that, you can also get the so-called water accounts. So earlier I showed you 6 times snapshots of those waters imagery. So you can basically map each pixel, how many times it was detected as water. So if it is 6, that means it's always there, so most likely permanent water. If it is 1 to 5, that means it's more like seasonal or temporary water body. So that means it's not there all the time. So it's very dynamic. So you have if you have a lot of imagery, you can do this just to calculate, for example, the dynamics of surface water body. The concept is like you can use the data, you can use cloud computing, and then you can easily extract the surface water from each imagery, and then you can combine them all together. Then you can see the dynamics. You can apply it to satellite imagery or other imagery. The idea is very much similar. I also developed a Google Sensing web app that allows you to actually utilize the cloud computing, also high resolution imagery, and also some LiDAR data that you can add, map the surface water body. You can also see the changes throughout the year. You can get the area, and you can get some kind of histogram. And you can also integrate LiDAR data, light detection ranging, to map these close surface depressions that can hold the water bodies. And you can check out the paper if you want to. So besides mapping the surface water body, surface water extent, we can also map the connectivity. So you can actually see how the water is moving across the landscape. So from the upstream to the downstream. So it's so-called hydrologic connectivity. So you can figure out where the water is going to. So from moving from where to where. And using the high resolution light detection and ranging data, so you can actually map out the surface water path. So on the left side here shows you some of the results from, for example, the thick blue line here represent the flow line from the national hydrography dataset. So those are national datasets that mapped out the surface water paths, but they don't capture those temporary ones. So those seasonal water paths or the temporary flow paths is not captured in those national dataset. So utilizing some of this high resolution data, area imagery, and LiDAR data, we can actually map out those temporary flow paths. And if you overlay that on the area imagery, you can see those flow lines actually coincides with those red color. So red color, this is the first color composite. So it's where the vegetation is growing. So it has high soil moisture. You can also figure out the maximum water extent. So you know if the water is increasing, you know if the maximum extent you can go. After a certain, if it's fully flooded, then the water going to move downstream. So you can get the whole flow network. So this demo just showing you all the data set. For example, this is the NWI, the National Wetland Data Set, and you can get delineated depression, so you can figure out maximum water extent. And once it's fully flooded, it's going to go to the downstream, so you know where the water is going out and where it's coming from. And you can also delineate the catchment, so you can get very fine detailed information about how the water are moving using this kind of satellite data and also cloud computing. So it's very easy to do, and as long as you have those data. So this is more like for focusing on the US when we have this kind of a high resolution data. But if you don't, we also, if you in other countries that don't have this high resolution data, we also have some of the global surface water data products available at the global scale. So the most popular one, probably widely used, is the GRC, the European Joint Research Center they developed, called Global Surface Water body data products. So it's based on Landsat data from 1984, and so they update process up to 2021, and 30-meter resolution. So we have monthly. So if you want to see the water in the past at any location on the globe, it mostly for large water body because it's 30-meter resolution, unlike the area imagery that you can have sub-meter. So this is for monitoring large water bodies. So historical changes. So you're going to see how it is changing. You can use these data products because it's very detailed and has been validated. So it has a very high quality surface water products. I will show you in the demo later how you can use that to analyze changes. And the second one is the ESA global world cover. So this one is delineated based on Sentinel-1 SAR data and also Sentinel-2 optical data. But it only has 2 time periods. So it's annual data product, 2020 and 2021. So you only have 2 images. But it's 10-meter resolution. And it's also very good quality. Also, the other one is the Esri global land cover. This one is solely based on Sentinel-2. It's also 10-meter resolution. Nice thing is that it has a longer time span. So from 2017 to 2023. So we have 5 time periods of data. And those are usually like basically low temporal frequency. So every year you only get one imagery. And keep in mind, surface water body changes all the time, especially for temporary surface water body. For permanent one, if you have like a boundary, a lake or something, it might not change like much. But for those free surface water body, it changes all the time. So 1 year, have one imagery sometimes is not enough. So if this is the case, then you might want to try out the dynamic world datasets from Google and World Resource Institute. And this one is based on Sentinel-2 imagery. And it's basically classify every imagery, every Sentinel-2 imagery that has cloud cover less than 35%. So basically it's not annual data product. It's just like when the satellite acquire the imagery, if it has good quality, less cloud coverage, it will classify the imagery. So basically you are getting kind of like daily, not really daily because the revisit frequency of Sentinel-2 A and B is right now roughly 5 days. So you can actually get kind of a weekly coverage. So in this way, if you are looking at more fine detailed high temporal frequency changes, then you might want to try out these data products. Again, it's all available on the cloud computing platform, so you can use it pretty easily. And so here, this is some of the snapshots from the website. So you're welcome to check out the website for more information. So the first one is the JRC Global Service Water Body. I will show you in another demo, live demo later, but you can check out the link. So this is where it's coming from, and you can look at any location around the globe. You can see the changes. You can figure out whether the water body is seasonal, or it's permanent, or it's temporary, and it's a monthly data product. It also has water accounts. So in this way, if you're working on flooding, you want to see, like, for example, during the last 30 years, has this area ever been flooded or not? Most likely you can use these data products to tell you, because we have all the monthly water exchange. So if this has been flooded, you will know when it was flooded and what's the area. And the second one is the ESA wall cover. Again, it has based on Sentinel-1 and 2 and different land cover. So this one is not specifically for surface water body, but because it's global land cover, it has the water class, so permanent water bodies, and also wetlands, and also some mangroves. So if you're someone working on those, you can extract the water class out from the global land cover. Similarly, the Esri global land cover, so it has a longer time span. So we have 5 time periods right now. And again, you can try it out. You can download it. It's solely based on Sentinel-2. So it's 10-meter resolution, but be careful. It's not really 10 meter because it uses some deep learning algorithms. So it's more like aggregation. So it's the reality is not really native 10-meter resolution. It's much closer than 10 meter. And the last one is the dynamic water data set. So this one you see here, it also has the water class. The first class here is water. They also have flooded vegetation, basically wetlands. So you can actually extract that one out. Like as I mentioned, this is like every Sentinel-2 imagery. So you can get 2 to 5 days coverage for any location around the globe. And you also see here, the visualization looks a little bit different because it compared to other data sets, this dynamic water data set also provide the probability, basically uncertainty. So you know each pixel, if it's classified as a certain class, you know how accurate it is. If it's really low, has a lot of uncertainty, you might need to be cautious. But the nice thing is that it has a higher temporal frequency, but you do need to spend some time to actually aggregate the data. So if you're trying to create, for example, monthly data, then you need to process data to aggregate and then get monthly, quarterly, or yearly. They don't provide the annual data products. So you do need to know some coding to do that. And Gmap has some functionality can help you create a time series pretty easily, just one line of code. So these are some of the background or some of the data set, existing data available for mapping service water body. So next, I'm going to introduce the Gmap, the Python package that I created. It's roughly 4 years now, and you can check out the source code. Everything is open source on GitHub. So it makes it easy for you to analyze geospatial data on the Google Sensing Cloud Computing platform very, very easily. It has been used by a lot of people. So last year, it was officially adopted by the Earth Engine team as the Python package that to support the visualization. So you can check out the Earth Engine documentation. You can see here the Gmap, the core. Basically, Gmap has the core component and also some extra. So the core component are co-maintained and developed by the Earth Engine team. So you make sure that it's stable and it's working properly. So if you want to learn more, you can check out the documentation website to see more details. So next, I'm quickly show you some key features. There are a lot to cover, but I will just show you some key ones. So first one, for example, you can search any data set. Just type link cover, and then you can just import the sample code and then run it. You will get the result. So this is kind of similar to you can search any movie on Netflix. You can search any videos on YouTube. And it's just one click, then you can stream the videos. You don't actually have to download the video. So very much similar in here. And this simple one can allow you to access over 100 petabyte of data. And it's not just for visualization. You can use it to do computation. So this is kind of the analysis that right now you are being. So Netflix give you the entire movie database for free. You're welcome to watch any movie. You can also download the movie. You can do some analytics on the movie. So, but in the geospatial domain, there are tons of data, and they all comes in different format, different projection, different types, different resolution, spatial, temporal. It's actually very difficult, but with this kind of tool, you can access to any tools, any data set, just a couple clicks, and that's it. You don't need to download the data, and you can just enjoy the cloud computing. So it's very powerful, especially if you're just new to geospatial, you want to explore some data. This can help you save you a lot of time trying to explore this type of data. It can be surface water, it can be land cover, temperature, weather, climate, you name it. So it's a lot of potentials. And you can also visualize data interactively, so provide similar functionality to desktop GIS. So if you have some raster data, vector data, you want to see it, you can do it very easily using the interface. So you don't need to know a lot of coding. Of course, if you know coding, that's better. But if you, even if you don't, you can create a map. You can load some data, as I showed you in the previous one, source some data, and then you can just use the toolbars to do some simple visualization. So very much similar to the desktop GIS. But keep in mind, this is everything running just in the cloud, just using a browser. And so for all the notebooks, actually there's a button here, open in Google Colab. So if you want to try it out, you do need to have a Google Sending account, but you can click the link, you can open it up, and then you can just start changing things. Very much similar to open a Google Docs. So the Google Docs is for writing text and report. Google Colab is more like for writing code. So you can use Python, you can use R. And again, it's just running in the browser, so you don't need to have things on your local computer. So you can visualize data. You can also, for example, query pixel values. You can create spectral signature, something like that. So allow you to actually access to the underlying data. So it's not just for like creating maps. You can actually access the original data. So this is why it's so powerful. For Google Map, for example, Google Earth, right? So those are just the base map. You cannot actually get anything. It's for visualization only. You cannot do analysis. You cannot download the data. You cannot, for example, figure out how many restaurants in your city. But for this one, you can, if you know how to do the coding. So if you have access to the original data. It also integrates desktop GIS, for example, QGIS, ArcGIS. So Gmap support ArcGIS. So if you someone that have been using desktop GIS, you can use them both. You can use both. So Google Engine or this cloud computing is good for doing computation, but they're not really good at making high quality maps or publication quality maps. So sometimes you still have to use desktop GIS, but you can use the Gmap and then to do all the computation, get the result, and then you can pull the data layer into desktop GIS, and then you can use that to create high quality maps for your publication if that's something that you want. So you enjoy the base of two worlds. You can create nice looking maps. You can also run large scale computation easily. And besides the 2D traditional mapping, you can also use 3D. So this is the one that I actually just added a couple days ago that allows you to visualize cloud computing data from Google Engine, any data set on a 3D. So you can actually visualize data easily like this. And it makes it more intuitive because it'd be nice to overlay things on 3D. So it can be lane cover, it can be lane slide, or it can be any data set. So now you can pull any data layer from Google Engine and then just visualize on a virtual 3D globe compared to just 2D maps. And again, you can try out everything here. I provide the link if you want to try it out. So these are some of the key features I want to show you. There are hundreds more on the website gmap.org. You are welcome to try it out. And So next, I'll show you this web app. It allows you to create time-lapse animations. So it's empowered by Google Sensing and Gmap. You can try it out on the website, on the link there. And it's very popular because you can basically create animation for any location around the globe. All you need is just go to the website, select an area in the images, and then you can just click a couple buttons. Then you can just create an animation. So within 20, 30 seconds, you get any animation. So it can be any location around the globe. You can use Landsat, you can use any other, many other satellites, and then you can download the animation. So this looks very simple, but without this kind of cloud computing, in the past, this can take you hours or even days to create. So imagine you're trying to create an animation for this location. You have tons of images. So as I mentioned, Landsat have 16 days. So every year you get, for example, every month you get 2 to 3 images. So right now, if Landsat 8 and 9, you get, let's say, 4 or 5 images. And for a whole year, you get hundreds of images. And you might have cloud, some might not have cloud. How do you create a high quality cloud-free imagery every year? And then for the past 4 decades, it's going to take a while because you need to download all the data, you need to filter, and need to run a lot of computation. So if you're trying to do this like using the traditional desktop computing, I can say easily, it can take you a couple hours. It's not like simple. But now, in 20, 30 seconds, you can do that for any location on the go. And you can use any data, any location, any time periods. It can be monthly, it can be quarterly, it can be yearly, you name it. So it's all customizable. So here are some of the striking examples that you can create. Again, on the left side here is the drawing of RC, so you can see how it's changing. Again, this only shows you the nice animations, but there are lots of science questions that need to be answered. So why this drying out, why this happening, and why this not happening the other way, right? And also mining in Canada, urban growth in Las Vegas. You can also see how the reservoir is changing throughout the years, and coastal erosion. So if you're someone doing geomorphology, like why the shoreline is changing this way, not the other way. And so loads of Landsat, but you can also do other data set, for example, MODIS data. So it's to monitor the vegetation changes at the continental scale. And you can create this again within 20, 30 seconds, any location around the globe. You can do that easily. For high temporal frequency, we also have other satellites, for example, the geostationary observation environmental satellites from NOAA. So you can use this to monitor weather and climate weather events happen very quickly. So we get data every 5 minutes, right? So you can put all the data together and you can create this kind of animation. So the volcanic eruption, wildfire. So not just for creating visualization, you can run this analysis. You can capture the area, you can analyze the data set, whatever algorithm that you develop. So these are some of the examples that there are a lot more. And I also published a book last year. If you're interested, you can check out the book, open access here on the link. But if you want a hard copy, you can also buy from the publisher. So there are a lot of features that allows you, can help you analyze those data, visualize the data, export the result, creating maps, and they also create this kind of web app. So the app that I showed you earlier, it's actually creating using those open source packages and Gmap, Stream, and also deploy on Hugging Face. So it's all free. You don't need to pay anything. And so if you want to learn more, this is all the packages that I created and maintain. So you're welcome to check out some of those packages. So Gmap is only one of them, and some other popular ones include leaf map, segment geospatial, and others. And also I have a lot of data catalogs that aggregating all the open access data in one central place. So you know, like, okay, I want to watch a movie. Where are those free movies? Sometimes it's hard to find. It's everywhere. So this might have you give you easy access to AWS data, Google Sensing, and also some open access data, for example, Maxar or NASA data, and also how to create web apps using some of the template. And I also created a Discord server. So you are welcome to join if you are interested in have some live discussion on utilizing some of those open source packages. I also have a YouTube channel that have a lot of tutorial teaching how to use cloud computing, how to do visualization using open source and also database. So you're welcome to check out the YouTube channel for more details, and also some workshops that I have done in the past. It's all recorded, so you're welcome to, if you want to learn more detail how to use those free resources, check out some of these tutorials. And lastly, I want to take a couple minutes to show you some live demo and something that you can adapt and then to do mapping on for your own area of interest using your own satellite data. So here I have a couple examples doing the flood analysis. You're welcome to check out the links in here. So like I said, everything reproducible. You can open the link and you take you to the website. I will show you later. So this is, for example, for the Pakistan floods in 2022. And I show you the step-by-step how you can use Google Sensing and Gmap to retrieve the data, extract the surface water extent, and then you can figure out what the area has been flooded. And it's very easy. You can just take you a couple minutes and you can easily adapt this to other area. And also the Brazil flood earlier this year, and almost recently the Dongting Lake floods in China just I think 2 weeks ago. And you can see the geometric changes of this area. And all the notable examples are available there, so you can try it out. So for example, here I can click and take you to the website here. And on the left side here, you can click some of those links. But on the right side, show you the table contents. So you're welcome to go through. We don't have, this one itself can be just one seminar, just showing you step by step. But you can just click the link here, for example, open in Google Colab, and then you can run this one on your own. So it's interactive. It's not just like for visualization. You can actually run analysis by yourself. You can change the area. You can do all kind of stuff, customization. And the map here, if you scroll down to the here, you should be able to see those data actually are still there. So these are from Google Sensing, right? So you can take a look at this one, right? So the set the imagery. So every code block basically does something. It'll retrieve the data, do some analysis, and then show you the result. You can also even have this kind of speed map to show you the changes. And this is running just in the browser. So there's because it's already rendered by Google Sensing, so we can still use the tile layer. But keep it in mind that the layer only valid for 24 hours. So after 24 hours, you might need to rerun it. So I'm going to show you the other better way that you can actually allow users to run things on the fly without having to do that on their own. So you can see the changes of the entire area that has been flooded. So it's huge changes in terms of the increase in surface water extent. And you can also, for example, just using a simple normalized difference water index to extract the surface water body. So you don't actually need to know a lot of complicated algorithms for this kind of surface water mapping. Sometimes the NDWI algorithm works pretty well. And then you can extract the water body. So you can see, for example, the blue one is the one before the flooding, and the red one is after flooding. So you can actually extract the surface water body extent and can calculate. You can see the changes. Again, you might need to zoom in. Sometimes the layer doesn't load up. So right now, for example, this cyan color is the flooded extent that compare this to time period after you after it has been flooded. So you can easily get something done like this, very easy, just within a couple of minutes. All you need to just customize your area. Then you can calculate the statistics. You can figure out what's the water area before the flooding, what's the area after the flooding, and then you can figure out, for example, what the difference is, what's the area that has been flooding. So it's not just a number. You can also get the spatial distribution, the location, the pixels. So those are using the Landsat data, but also we have SAR data, basically different type of data for doing mapping surface water body. I don't have time to get into the details, but you can try out. SAR data is a little more difficult to interpret, but it can certainly be used to map some of those surface water body. But you will need to do some pre-processing before you can actually, for example, some spatial filtering, and then basically reduce the noise of the data, and then eventually you can map out some of those changes. For example, here you can still see some of those. It's not going to be the same as the optical data because it's SAR data, so it's different. Then you can do the same thing. You can extract the surface water body. You can calculate the extent, something like that. So you're welcome to adapt this to your area. Again, all the examples are here, and it's all free and accessible, reproducible. So the last one I want to show you is a new one that I just developed. So this one here has a web app and also a GitHub repository. So if you want to see the source code, you can check out the GitHub repository here. I'm still working on that, but you can see all the source code available. So if you want to develop on your own, you can check out some of the source code. For example, create a time lapse and then how to analyze the data, how to create a time series, how to compare. It's not that complicated, but you do need to know some coding. But I already had the web app, so I'm going to show you here how to use this one. This is just for demonstration. It's not like for production because you're using my Google Sentinel account, so it's not for commercial. But you can try it out. So it makes it really easy to use. So I'm going to show you some examples how you can actually utilize this one. So you can create animation. So if you are interested in create animation, so I can, for example, just open the web app and that's it. So you don't need to know coding. You can zoom to anywhere around the globe and you can start creating animation. So you can turn the layer off. So if you are interested in a certain area, let's look at, for example, this um, area in blue, right? And after that, all you need to do is just simply draw reason interest. So imagine, okay, I'm interested in this area. I want to create animation of this area. You only need just draw a rectangle, and then that's it. You don't really need to do anything else. You can also, for example, I want to extract the water. I can just click the surface water NDVI extend. So hopefully it works. Sometimes if too many people are using it at the same time, it may not work. Let me see here. Yeah, sometimes it's frozen because it's too many people, but let's see if it works. It might take 20, 30 seconds, so it's not always. If it doesn't work, you can refresh or you can try it at a later time. And you see it's not working, so probably it's too many people. Sometimes it's refreshed. But anyway, let me try the other one. So this one might be a little bit better. So I can show you, for example, I can go to any location on the globe and assume that right now I want to look at some of the satellite imagery available for this location. So what I can do is like I can search the area and, for example, RC is the one that I am interested in. So the animation that I showed you earlier, right? So now if you look at this, this is the area, for example. I want to see the changes of this location during the last couple of decades. So all we need to do, I can just simply draw a rectangle somewhere around this one, this area. And then we can use Landsat. So as I mentioned, right, Landsat has imagery from 1980 to right now. So we can create imagery, for example, by year, by quarter, by month. So right now, assume, okay, I want to do it by year. So you can easily create it and take a look. The first one here is 1984. So it's like probably not full coverage. So let me change to 1986. So now take a look. So we have the imagery for this location since 1986. And there should be a time slider. So let me zoom in a little bit. So if you maximize the screen, you should see a time slider here at the bottom. So this one shows you, for example, 1986. Take a look, 1991. So you have access to the original data. So this one is unlike the animation. It's only a very close resolution. This one you can actually zoom in, so you can see all the data during the last couple of decades. And like I said, you don't need to know coding. You just use the web app. And let's go to what it looks like right now in 2024, right? So the background imagery is the Esri wall imagery. So I can turn it off, and now you can see the changes. It might take some time to load, but you can see the dynamic, right? So this is showing you the changes, yearly changes during the last four decades. And you just streaming the data, you can zoom in, you can zoom out. It's actually very high resolution. So this is 30-meter resolution Landsat. It can be anywhere. It doesn't have to be this particular location. It can be anywhere around the globe. You can also do it by, for example, by quarter, by month. So if you're interested in a monthly water body, you can also by month. But it's going to be tons of data, so you do need to be careful. Otherwise, you exceed the memory. So for example, I can look at the data, monthly data from, let's say, from 2022 to 2024. And then I can create a time series. And I can see for monthly, sometimes the quality is not very good. So you do need to basically find it out. But it's super flexible. So under the hood is using cloud computing to create this imagery. And you can do it like this. All right, so you can see the monthly changes pretty easily. And so let me go back to the previous one, and I'm going to show you here. The other one is more interesting. Also, you can use the split map. So let me remove everything. So if you're interested in this area and you want to compare the changes, I can also create a time series and then use the split map. So what does the split map do is actually showing you the images, and then you can use the slider to change it. So let's look at, for example, 1986. And this is the imagery from 1986. The one on the right here is 2024. So you have different tools that can help you do the visualization. Again, this can be anywhere around the globe. It doesn't have to be water. It can be anything that you're interested in. and you can just use the tools to actually visualize the data. So before you're trying to do some scientific research, trying to find out like what has changed during this, you can easily use this one to create animation. And then, so that means you can also close it. So once you're done, you can, there lower right corner here, there's a button. So you can just close it off and then it's gone. I can try another area. For example, I say Las Vegas, okay? And so you can go to, go to Las Vegas here. All right, so assume that you're interested in urban growth, right? So I can also draw the area, and same thing, I can just split map. So you're going to create annual imagery for this area for the past 4 decades. And all we need to do, you see, so now we have data from 1984 to 2024. So these are all powered by cloud computing, Google Sensing, and also Gmap, and it's super easy to use. Again, it's anywhere around the globe, and you have tons access to the entire Landsat data catalog. It can be Landsat, it can be Sentinel, it can be any time series. So all you need to do is just customize the source code. Next one is the JRC dataset. So this one also allows you to see the changes. So if you're interested in changes of any location, for example, let's say, okay, I want to see the data around, for example, North Dakota. Okay, I'm mapping the wetlands. I'm interested in this. So I can zoom to anywhere around here. And then same thing, I can draw a rectangle. So I can find out an area of interest. For example, I'm interested in the changes of this lake, particularly in this area. It can be a polygon, it can be a rectangle, it doesn't matter. So all you need to do is just click the accounts. So it's going to show you basically the temporal dynamics, basically the frequency. So you can see this particular water body here, how many times it was flooded is, for example, basically every pixel. How many pixels were flooded 100% of the time? Some like 75%. So you can certainly see this is more like a dynamic source water body. It changes throughout the year. So this is the data aggregated from 40 since 1984. So it's almost 4 decades of data, and this is aggregating all of them. But you can also see the monthly history. So monthly means like you can see the water extent during the last 4 decades. So you can see whether the water is increasing or is decreasing. You might see some anomaly here because monthly data sometimes have cloud. If you don't have good data, then you might end up with something like this. But of course, you can try out any other location. For example, if I go to the ROC again, and you will see in this particular area, right? So this leg in here, earlier I showed you already saw that it's huge changes. So let me reset in here just to show you how do I analyze this one, right? So I turn on this one, and I can draw a rectangle here. So assume that you're interested in this area, I can look at the monthly history. So I can show you how the water has been changing in this particular area. It can be a lake, it can be a country, it can be a continental. So you can adjust some of the parameters in here. I can also adjust the months. So if you're only interested in the summer months, then you can use, for example, June to August or something like that. So the larger the area, the longer time it's going to take. So you also might, sometimes it doesn't work. If it doesn't work, then you can refresh it and then just open it again. So you see here, this one takes a little bit longer. It might be more people using that. So sometimes it makes out the connection. So Google essentially doesn't allow you to have too many concurrent connections. So sometimes it might take some time. Anyway, so there's 4. You see it's not working. I will show you later, but I think the last one I'll show you, let me refresh it a little bit, is the compare. So this is the one, whoops, interesting. Something's missing. Anyway, it's not supposed to be here. It's just a bug, but I can show you what this one is about. So this one can allows you to analyze the changes for the flood mapping, right? So as I mentioned earlier, so let me show you here, right? So earlier I showed you the Dongting Lake floods. I think it's, where is it? Here. For example, right? So this is the flooding area that I showed you earlier in that notebook, right? So assume that something has happened, and you want to quickly use this to do the mapping. I can just go use this web app, go anywhere around the globe, and just simply draw a rectangle. And then you can tell it what's the date of the imagery that you want to use. For example, I can use the data. They said, I know this one started from this flooding happened in July 5th. I think July 5th or 6th, right? And up to right now. So I can say, okay, this is the post-flood area analysis. And then I can also use the data from, for example, I would say this is, I can use data, for example, from 2024, January 1st, and then to, oops, maybe 01, 01, right? 2024, January 1st to July, and then maybe July 4th, right? So right now I have this data and I can quickly, for example, I can apply just to quickly show you the imagery, the set the data for this area, and hopefully it will work unless there's too many people are using that. But it will actually allow you to quickly get the imagery and then you can compare them side by side. Also, you can actually extract the water, so you can actually compute the NDWI. You can set the threshold. Let me see here. It doesn't work right now. Let me see. Yeah, it's not supposed to take. Sorry. So this one should be 2024. I think I missed something here. But let me try again quickly. So again, I'm going to zoom to this area, or you can just do the search. I can show you what it looks like here. And I just want to show you the power of this cloud computing. So it's so January, and then this one I want to show to 2024, and similar this one is 07, and then oops 0704, and then 2024, and the next one will be 07 July 5th, 2024, and then up to right now, and let's see if it works. Okay, so take a look. So now this is like pretty easy, right? There's no coding. You can just use this. And so let me remove this extent. So this is the same one that I showed you in the notebook, but right now we are doing it interactively. So there's no really coding that you need to do. So you can use whenever there's any flood happening, you can use this web page, just quickly get the data from Landsat and then you can see the changes. And nice thing, you can also compute the NDWI. So you can actually extract the water body. I can just click, run it, and take a look. Everything can be done in seconds, right? So I don't need to have a fancy computer. I can see the new water, for example. This is basically the new water is the flooded area. And also you can see the disappearing water. This is mostly for those water body that shrink. And you can see the post-event water, the pre-event water. And you can also see the imagery, for example, before and after, right? So this is the pre-event, looks like this, right? And this one is the post-event, looks like this. And then this will be disappear. Of course, the algorithm is not perfect. It's just a simple thresholding algorithm. You can create better algorithms if you want to. But I'm just showcasing you how do you do this kind of analysis just within a couple seconds, and you can do that for any location. You can just roll a rectangle anywhere around the globe. It will just work just fine. And so this is some of the data set you can utilize, but let me reset. And so assume I can do the same area. I can also create a split map. So just click one more time here, right? And take a look. So this is the one that I showed you earlier in the notebook, but right now, again, we are doing it interactively. We are not doing that for other locations. So similarly, right, I can just, oops, zoom in here. Once you're done, you can close it. So upper right corner here, there's a button, you can close it, right? So similarly, you can go to any location. So if you know what is happening, for example, around a certain area, then you can certainly use this one just to filter the data and try it out. For example, I can show you one more time here. Just like what I showed you earlier, right? I can go to here, I can draw a rectangle, and then you can showcase the changes, right? So for this one, I can do, for example, 1998, okay? Another one, 1998, oops. 1998, right? So for example, just want to compare the changes. You can compute the water body if you want to, or you can just do the split map, okay? And then apply, then you should be able to see the changes, right? Again, so see this, right? So literally, there's unlimited potential. You can try it out for anywhere. Anyway, I don't have time to go into detail, but you're welcome to try out, and all the source code are freely available, so you can try it out on yourself. And if you have any questions, feel free to reach out to me. And thank you very much.
Wow, that's quite a lot to grasp in so short a time. But a few quick questions. How can, wow. Where can we access the link? I think you have touched on that.
The link is here. So let me go back to the beginning. So if you miss it, it's here. So this is the link to the slide and also the QR code here. And all the links are public accessible. So you're welcome to try out all the resources that I provide in the slides.
Okay, another question. The person is working on water quality, and I guess that flipped my reaction too. Whoa.
Yeah, you can do anything.
Is it possible to use any of this to get water quality parameters?
Yeah, you can, right? So this platform shows you how to access the data. The algorithm is up to what you want to do. You can be water quality, it can be soil moisture, it can be anything. You just need to define your algorithm. So particularly for the water, right? I just use the simple NDWI to do the thresholding, but they are more complicated algorithms. So all we need to just figure out how do I. It's kind of like Lego. What you want to build is up to your imagination. But we also already have those blocks for you. You can do anything you like, but you do need to come up with the algorithm how to map the soil water quality. You can check out the literature. There are already tons of people using Google Engine to do water quality analysis. And there are a lot of publications. And also there might be already some existing web app available. So you can check out how people are doing that. And then you can just adapt. And then because all the source code Google Engine, most likely, if they have the JavaScript or Python, it's already something developed. You can build on top of what other people have done, just like the web app that I provided. You don't need to start from scratch. You can utilize what I already built, and then you can customize to your area or for particular floods or whatever you like.
Thank you. Yes, for all the people that are asking whether we are going to share this presentation, definitely, check our website, you can also get the presentation or the link, just take the QR code, scan the QR code, and follow the link. But we also share it on UNU-INWEH website. Wow, it's been interesting. Thank you so much, Dr. Wu. We are really, grateful we can get over the technicalities and have this presentation today. And hopefully very soon, I believe by popular demand, you may have to come again. But on behalf of myself, my director, the whole UNU-INWEH family, and of course the public, we say thank you for the presentation. And to everyone who are taking time to participate today, thank you for joining us. Let's see you again next week. Thank you.